Okay, welcome again. I'm going to do, this time I'm going to show execution that can start on arbitrary abstract representation states, and I'm going to change the example to rebalancing the red-black tree after a delete. So when we rebalance the red-black tree after a delete, we get a shape like this. We have some node of some color, we don't know what, and we have one side is black length k and the other side is black length k plus 1. So we start off by trying to get a bunch of black nodes on the screen. So we're going to go down on this guy to say, okay, well, this is just k plus 1. We'll expand that out to these two k nodes, and we want these two k nodes to be black also. We want this p to be black. So we expand that out, and now we have everything is black. Now we can go ahead and deal with that. So we deal with this case first, which is basically recursion. So we make one node red. So we go in the direction of making a node red, and then we recurse back to the beginning, or loop back to the beginning. For empty, we just make one node red and return. Okay, and now we have this shape over here. With this one is really easy. We just flip we flip these colors, and then we have a red-black tree, and we can return. This one, again, we're going to use some rotation. So we have star star here. We just want to make it a much more regular tree shape. So we go ahead and get rid of the wildcard axes and replace them with alpha, which allows us to do a rotation. And then we just flip this color. So this goes, the unknown color was flipped down, and then now we just flipped it back up to S. And we make this black, and then we can compress this into a normal red-black tree. And the other side of that alpha is just one extra rotation, and then we can loop back up to the first case. And notice that this loop back does some variable renaming and also flips some colors. So we go from here, we flip the S and A color, and then we also flip their variables. Okay, so now the last case, or we're getting to the last case here. We have still quite a ways to go. This kind of looks like up here, except the axes are flipped. So we're going to make that a black K by expanding it and by branching. And now we can just loop back to that case up there. Okay, and then we have these two things where we're actually going to have to do some rotation here. So let's go ahead and get rid of the wildcards by turning them into alpha so that we can enable rotation. We're going to rotate S up. Then we're going to make S the unknown color. And all we have to do is color B black, and then we can compress this. And the other case is just, they're the same because B and A are just swapped, but they're the same color anyway. So we just can loop back up to that first case directly. Finally, we have our final case where the original k plus 1 was actually red. And in that case, we just rotate the S up, swap the colors of P and S, and then we compress this into an unknown P, which has the shape of our original problem. So we just loop back up to the black case that we had at top. Okay, so does this actually work? Well, let's go ahead and execute it. So let's start at the top, and we'll run execute. Let's try to find something smaller. Right, so here's an example where P is a black node. We're going to execute, run the first instruction, which is the switch, and we find out that its child is, this k plus 1 child is black. We expand out the k plus 1 construction, and then we find out that its left child is actually red, and its right child is actually red too. So we get to this shape over here, and we do the alpha check, and they're both the same axis, or we do the axis check, and they're both the same axis. So we go into the first case immediately. And then we rotate up S, and we swap some colors around, swap P and S, and turn B from red to that, and then that's it. We're done. If we count the black length here, we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We have 1, 2, 3, 4, 1, 2, 3, 4. So this tree is balanced. Okay, and then we return. So let's go ahead and look at some stranger examples. So we can actually go ahead and we can select any sort of state we want, and we can generate a tree from there. So let's look at this case, right? We see exec. I'm going to generate something smaller just so that we can see what's going on. So here we have the case where we do the axis check and they're different sides. So we do the rotate A up in that instruction, and then we just go to L1, doing some renaming and some recoloring at the same time. And then we go back to the first case and do the rotate, the first case up here, and then we rotate S up, and then do a little bit more recoloring, and we're good. So we can explore some more of the esoteric cases, like up here where we actually loop right away. So let's look at that. Okay, so here we have A is our A is our node. We don't care what color it is, but it's actually red. And P is a black node, and S is also a black node. Right, so we have those over here. So we do the flip colors on S, making S red. Sorry, I have to click down here, otherwise it doesn't happen for real. Okay, then S becomes red, and then we just compress, but that just takes away the two variables from the thing, and then we recurse back up to the beginning again, where is making where A becomes P, and then we are at the top again of the balance routine, and we fall through where S is black. We expand out S. We find out that we have our left child is red, and our right child is red. So we just go back and we swap the A and B, and then we're in the first case here, and then we just rotate up S and flip the colors, P and S, and flip B. You can see it here. And then we do compressions, and then we can check to see, well, is our tree the right size? So we have 1, 2, 3, 4 length on this side. We have 1, 2, 3, 4 length on this side. All right. We can go and actually look at this case over here, which is a lot weirder. We click that, make sure it's back at the first thing in and say exec. Right here we have our node is red right away. So then what happens is that we rotate up, sorry, to click this one up here. We rotate S up, and then we flip the colors. Then we do a little bit of compression and focus on P. We know that P has two children. One is K plus 1 and one is K. So K is here in this case is 1. And so K plus 1 is 2. Right, and so we're just going to go back up to the top, up here, and then we look at the next one and we find out, yeah, our K plus 1 child is black, and expand that out. A is red, B is red. We've seen this one before. Compare the axes. Rotate up S, recolor, and we're done. So we have 1, 2, 3. We have 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, and that's about it. Let's see. So you could just we can look at any weird corner case that we want. I don't know if we actually haven't seen one yet. We can look at one of the simple ones, which go empty up here. Right. So let's go and exec that one. Click on that one for sure. Right here is just a simple case where we have it's k plus 1, but k and k plus 1, but the root is empty, p is at the top. So then we just turn that other color red, and then we get a 1, 2, 1, 2 tree. Okay, that's it. Thank you.